today we've got some exciting things we're going to go through, and you know what? Let's speak to the master himself. He's going to tell us.
Right, guys, we're actually doing some physics tonight. We're going to be looking at work and energy. So grab your notes. What are you doing?
Yeah, I'm getting full of
Is
energy.
that the work?
This is energy, the work and energy.
Okay, Leanna's on her own little mission at the moment. But guys, grab your notes, grab your exercises and things like that. I'm going to be going over the basic concepts of work and energy with you, doing a couple of examples on the board, hopefully making things a bit clearer.
Noxipedia said, what do we exactly mean by vector quantity?
Okay.
And what I love about this, Bruce, is that if you guys' mindset is go and have a look on the page, go and see Noxipedia's comment, and you'll see that there have been other mindsets that have answered it for us. But I mean, I'd like you to go through it to see if they're right.
Guys, when it comes to quantities, measurements, and things like that, we have two types of quantities. We have what is called a scalar quantity and something we call a vector quantity. Okay. Now, you guys are sitting in grade 12. You probably would have had this introduced to you in grade 10, definitely in grade 11. So I'm hoping that this will be pretty much a revision exercise for everyone. A scalar quantity is a quantity that does not have any direction. It's got magnitude, yes, we can measure it, but it does not have direction. A vector quantity, on the other hand, has got magnitude, but it's also got a direction. Now, I'm going to do a very short example just to make sure that we do understand it. If I'm starting at let's get this pen up. If I'm starting at point A, okay, and here is point B over there, okay. Now, I'm going to move, I'm going to pretend I'm in a car and I'm going to drive from point A to point B, and I'm going to jump in the car and I'm going to take off. I'm going to climb a couple of hills, take a few left and right turns, and what's going to happen is that, boom, I'm going to arrive at point B. Can you see now that I have traveled a certain distance and I've followed the route length, or let's call it the path, okay, from point A to point B. So, for example, if I was going to Durban to Joburg, I would jump on the N3 and off I'd go from Durban to Joburg and I'd follow the road. Okay. However, if I actually was in an aeroplane, what I probably could do, in fact, I'm going to do this in a line here. No, it's not going to work. If I was in an aeroplane, I could actually take off in the aeroplane from point A and I could go in a straight line all the way to point B like that. Now, can you see that I can measure the path length from point A to point B? But can you see now that I have got a specific direction that I have traveled from point A directly to point B? So therefore, what we call this is our displacement. Okay, that's a displacement. This sort of roundabout way here, this path here, is called a distance. Sorry, I'm just going to grab some water quickly.
That's okay. While you're having a sip of water, Pusaletso wants to know what happens when the force and displacement are at an angle to each other, as opposed to the squiggly. Would it be the same?
And what I'm going to do straight after this, I'm going to look what happens when we have force at an angle and how work is calculated with forces at an angle.
Okay.
Okay.
Perfect. Fantastic.
I just want to quickly finish this one off. So can you see now that the path length is the actual distance? There's no real direction. It's all over the place. It's up, down, over the hills, left and right turns. So this now is what we call, let's get this, sorry. This is what we call a scalar quantity. Okay, so distance is going to be a scalar quantity. When we go in a straight line from A to B, that is what we call a vector. Okay. I'm sorry, I think my cold sort of got my throat a little bit, but I'm getting through it, so don't worry guys, I'll make it, don't worry. So there now is my vector quantity. Displacement has got magnitude. I can measure from A to B, yes, no problem. But it's got a direct direction from A to B, that's what makes it a vector. Okay.
Fantastic. Cool beans.
Right, and I think we wanted to chat a little bit about those angles, eh?
Yeah, should we?
Right, I just want to scroll that down. In fact, let me just get a new page up. And so give me a little bit more space. Now, guys, there's been a couple of questions. Is what happens now if the force that's acting on the object acts at an angle to that object? So I'm going to draw exactly the same. I'm going to draw exactly the same diagram, but notice now, guys, I have not put my applied force in the same straight line or parallel to the direction of motion. I have now drawn it at an angle, which I'm going to just mark in like this, at an angle theta to the horizontal. The important thing, guys, is that the word I use there is absolutely crucial. I have drawn in the angle theta to the horizontal, which means, guys, is that although my force is acting at an angle, the object is still going to move horizontally, which means, guys, I have to now use what is called a horizontal component. I have to use what is called a horizontal component. Now, again, we're calling on your knowledge of grade 11, because when you guys did forces in grade 11, you would have been told about how we resolve forces into components. We have two types of components. We have got vertical components, okay, which I'm going to draw in like that, and we've got horizontal components. So I'm going to do it like this. I'm going to call that VC. I'm going to call that HC. Now, all a component is basically two forces, in this case forces, at 90 degrees to each other that represent the combination of the force, the 100 Newton force at that angle. So what we have to do now is somehow be able to calculate the horizontal component. We are not interested in the vertical component. Very importantly, and the question comes up, why don't we include the vertical component here? Because, guys, the force must act in the direction of the motion. Okay, and work is only done if the force is parallel to the direction of motion. The vertical component is not in the direction of motion. In other words, can you see now that the vertical component is at 90 degrees to the direction of motion? And any force acting at 90 degrees to the direction of motion cannot result in work being done. Okay, and I'll say that again because it's also a very important part of physics here. Any force acting at 90 degrees to the direction of motion, no work can be done by that force. Okay, we have to make sure that our force is parallel to that direction of motion. Which means, guys, is that over here, we have to now calculate our horizontal component. And the big question is, how do we calculate that horizontal component? And here now, guys, a little bit of math skill starts coming in. And what we're going to look at is a little bit of trigonometry. So, what I'm going to do...
Nguako, you are so right. You already said, are you going to be tackling trigonometry?
Okay, right. There now is my force, my 100 Newton force. There's my angle theta. So I'm going to write it in, 100 newtons. Now, what I'm going to do for trig is that I'm going to take that vertical component and I'm going to complete the triangle here. Like that. In other words, that's my vertical component there. This is my horizontal component over here. Now, with trigonometry, what do we need to do? We need to label the sides of that triangle. Remember, guys, it has to be a right-angled triangle. And yes, we have a 90 degrees between vertical and horizontal. So we've got our 90 degrees, our right-angled triangle there. We've got an angle theta, which is the angle between the horizontal and the applied force. So this now becomes known as the opposite side. This now becomes known as the adjacent side. And you'll all tell me now that, that the other side becomes known as the hypotenuse. Okay. Now, if this is the adjacent side, in other words, the adjacent represents the horizontal component, and we know the value of the hypotenuse, what trigonometric function is going to allow us to include the adjacent in the calculation? And hopefully all you guys are jumping up and saying the cos function, cosine. So cos theta, okay, is going to equal adjacent over hypotenuse. Okay. Now, what does that mean? Well, if it's adjacent over hypotenuse, the adjacent represents the horizontal component. So I'm going to call it, whoops, the pen's just not behaving too well at the moment. There we go. I'm going to call that FHC, the force of the horizontal component, or should we rather say horizontal component of the force, which is going to equal the hypotenuse, which is the applied force multiplied by cos theta. And there, guys, is how we calculate, so that's an A over here, that is how we calculate the magnitude or the value of the horizontal component of the force when the applied force is acting at an angle on that object. So let's have a look at a problem. Let's do a problem together and let's see what we can do. So let's scroll a little bit here. Things not moving too much. There we go. Right, so what I've got a little problem here to do with you guys. And what I'm going to do is take my object. I'm going to put in my 100 Newton force there, and I'm going to make this a 60-degree angle. Okay? The object is going to move, displacement is going to be 10 meters. Okay? And let's see how we do it. Well, here we go. We've got a 60-degree angle. We know that the work done is going to equal the force multiplied by the displacement that's going to be covered. Okay? But because we're now at an angle, we have to now use my horizontal component. So I'm going to put there HC times my displacement. Right, let's work out my horizontal component. So it'll be, HC is going to be F applied times cos 60, which is going to equal 100 times cos 60. And cos 60 we all know is 0.5. And therefore, we're going to find that my horizontal component is going to equal 50 newtons to the right. Okay, again, I'm keeping compliant with my vector quantity. Force is a vector quantity. I must put in my magnitude and direction. Now, simply substitute that in over here, and what do we get? We get 50 times, where we're going, delta x is 10, and can you see now that we are now having, the amount of work is going to be 500 joules. Now guys, I've used exactly the same values that I did with my previous question, and we know that the previous question came out to be 1,000 joules. So can you see now, by having an angle of 60 degrees, the amount of work done on that object has actually dropped by half. We've only got 500 joules of work. So therefore, where does that work go? That work is going to be transferred into kinetic energy. And the kinetic energy is then going to cause that object to move at constant velocity. Okay? And if it moves at constant velocity, then we know that work done is equal to the gain in kinetic energy, and therefore the work done, which was 500 joules, is going to be a half mv squared, and therefore substituting in 500 equals a half times the mass, and we made the mass, sorry, there was 10 kilograms, times v squared, so that's going to be v squared will equal, divide by 5, 100, and very simply to square root 100 would be 10 meters per second to the right. And there, guys, is how we can work out the velocity of that object. One other thing I wanted to have a chat about before the end of today's show is going to be having a look at friction. Now, at the moment, I've been talking about frictionless surfaces. We've spoken about the forces acting in the direction, parallel to the direction of motion, therefore causing work to happen. And we've also looked at the applied force at an angle on the object, but then we're having to calculate the horizontal component. But what happens now if we have friction? We bring friction into the entire problem. Again, last year, grade 11, you'll remember that when we did Newton's laws, we also looked at bringing friction into the whole equation. How do we do that now when it comes to work? Well, it's very simple. What I'm going to do is draw on my block. There's my 10 kilogram block. Okay, I'm going to keep this now in the horizontal plane. Okay, and I'm going to now introduce a force of friction. Okay, and we must remember, guys, that friction is a force that always acts in the opposite direction to the direction of motion. So if I've got my applied force acting in this direction, okay, then the applied force is going to cause the object to move, then my friction must be acting to the left. And that becomes very significant because, again, we're introducing that vector part, or the vector considerations into these type of calculations. Again, so what I do is to make life simple for me. As soon as I get friction or something acting in the opposite direction, I like just to put in my arrows to remind me which direction I'm taking is positive and which direction I'm taking is negative. Personal preference, I generally like to make to the right going to be my positive. Now, guys, let's have a look. There I've got 100 newtons, okay, and 100 newtons acting to the right. Now, this object, I'm going to tell you, is moving with constant velocity. Okay. Now, we had a little Twitter question, or I think it was a Facebook question, a bit earlier, where we said if the object moves at constant velocity, then the forces in the system are in equilibrium. They are balanced. So straight away, what you should be able to tell me now, that if the object is moving at constant velocity, okay, so yes, work is being done because the object is moving to the right. What is going to be the magnitude of my friction? Well, if the forces are in equilibrium, then my applied force must be equal to my frictional force. Okay, which means then that the object is going to have work done due to the applied force as well as work done against the motion, because it is moving, so work done against the motion, the work done due to the frictional force. And therefore what we can introduce is what is called applied work, okay, which is going to be the work done due to the applied force times the displacement, okay, and then we can have the work done due to the frictional force, which is work, F, which is frictional work, which is the work done due to the frictional force multiplied by the displacement that the object is covering and experiencing that frictional force. So guys, we are now introducing different types of work into the system. The applied work, okay, and the frictional work. Okay. Now, what happens, okay, if we have this? Let's extend it one more. There we go. Let's take my object. Okay. Let's put the object onto a different surface. In other words, there's my 100 newtons acting to the right. I'm going to change my surface, and my frictional force is now only going to be 20 newtons. Okay. Can you see now that my applied force is right in there? Oh, goodness, it's jumping around a bit. My apologies. My applied force, which is equal to 100 newtons, okay, to the right. Our frictional force of only 20 newtons to the left. Can you see now we do not have an equilibrium? The forces are not balanced. Now, remember I used it earlier on in the show. What do we call a force that is not balanced? Well, an unbalanced force is known as a resultant or net force. And how do we calculate that? Well, we have a net force. Is simply adding the forces in the system together. So it'll be F applied plus the frictional force which is going to equal, well, remember, to the right we're making positive, to the left we're making negative, okay? So it's going to be plus 100 plus minus 20. Whoopsie, I nearly put down 50, my mistake there. Sorry, let's rub that out. Bring back the pen, here we go. Plus minus 20, which, quick maths, 100 minus 20, we have got a resultant force of 80 newtons, or a net force of 80 newtons to the right. Okay, now, remember guys, what do net forces do? Net forces cause acceleration. So this object is now going to accelerate, okay, which means then that the work done, okay, is going to be due to now what is called a net amount of work. Okay, so what we're going to have is W net, the net amount of work, is going to be due to the net force multiplied by the displacement that the object covers. And now we've introduced what we call a network. And this introduces something that is going to be almost 100% guaranteed to come up in your exam at the end of the year. And that is known as the work energy theorem. The work energy theorem. Okay.
You know, Bruce, these mind-setters, they get, I mean, I've gotten Bailey on here, and she's saying to me that, you know, she gets there's so many terminologies that she has to learn. I mean, how do they learn these terminologies? The best thing is to write them down, I suppose, and learn them off by heart.
In two ways. Okay. Number one is to sit down, write them down, learn them as definitions.
Yeah.
You're going to be asked definitions in the end of your exam. The next one, and I think is probably the more important, is to practice problems that involve all these different types of work dones and things like that. So we've got applied works, we've got frictional works, we've got networks and things like that.
Yeah,
and
exactly.
The work energy theorem is actually a very important theorem that allows us to look at the net work within the system. Because, guys, net work is calculated through a net force. A net force produces acceleration. Now, what happens if an object accelerates? Well, the velocity is going to change. So, therefore, what we're introducing now, if the velocity changes, then the kinetic energy is going to change. So, if I have an object over here, okay, and it moves to this point over there, let's call that point A, and this point B, okay, and let's say it had a velocity of 10 meters per second, and over here it's got a velocity of 15 meters per second. Straight away, guys, can you see now, for the velocity to change from 10 meters per second to 15 meters per second, we must have had a net amount of work, or a resultant force, should I rather say, acting on that object. The resultant force has produced the acceleration, and therefore the resultant force has caused the velocity to increase. So, if we had to look at the EK here, which is a half mv squared at that position, and a half mv squared at that position, I'm going to call that EK initial, I'm going to call this EK final, okay? Can you see now we've got two kinetic energies, which means then we have got what is called delta EK, a change in kinetic energy. Now, what does the change in kinetic energy equal? Well, it must equal the net work done. And that is one of the very important components in our section on work. It's called the work energy theorem. That the net work done as a result of the net force in the system is going to cause a change in kinetic energy. And this change in kinetic energy allows us to do the net work. So, for example, if this was a 5 kg object, okay, we could very simply work out the initial kinetic energy, because we've got mass and we've got velocity. The final kinetic energy, because we've still got the mass, that hasn't changed, times the velocity. And then delta EK, and and very important, is always your EK final minus your EK initial. And that delta EK will equal the net work done in the system. And from there, extend the page. I know it's very theoretical at the moment, but we know that W net is equal to the net force times delta X. Okay. From there, we can then calculate the net force, and from Newton's second law, F net equals ma. We can actually calculate the acceleration. Can you see, guys, it's a bit of a sequence of calculations, a bit of a sequence of mathematical equations here. And that is why the examiners love this type of question, because they can now start adding all sorts of things to it. So ultimately, what we've got to try and do in our next Sean work is to actually do problems, do some examples associated with the work energy theorem. And once we can do that, then we'll be able to practice these and see how this whole thing works. Okay. Anything else on Twitter and Facebook?
Twitter and Facebook, Bruce, there are a few. Okay, I know the producer said we've got about 3 minutes.
Okay.
So let's get through them. And I see Lebza, I see you're getting there. She was a bit confused, but now she's understanding. Go, girl.
Okay.
Okay, let's have a look. Let's see, over here. Sure, there's so many questions. Okay, this one's from Ngwako. He said, total work done by an object is equal to change in kinetic energy of an object. That law is expressed mathematically by this equation. W net equals EK.
Delta EK.
Delta EK.
Yeah.
And is that correct?
Yeah, it's the network. Remember, so what was the guy's name?
This is Ngwako.
Ngwako, remember that if your kinetic energy changes due to a change in velocity, okay, then you've got this resultant or net force. And a net force always produces an acceleration, either a positive acceleration to make the object go faster, or a negative acceleration to make it go slower. Okay, so in Ngwako, just realize that when we have this change in kinetic energy, we're looking at what's called the net work done, because the net work done is directly as a result of the net force that's in the system, that's creating this change in kinetic energy. Okay. I'm sure that'll help.
Fantastic.
Yeah.
Okay, and Buddy wants to know, what is a non-zero resultant force?
A non-zero resultant force. Well, a zero resultant force is a resultant force that is zero. Now, what does that mean? That means that your forces are in equilibrium. Your forces are balanced. So are you going to have acceleration in a balanced system? Absolutely not. That object will either remain at rest or will move with constant velocity. No change in velocity at all. Okay. A non-zero resultant force means that your resultant force is greater than 1. And if anything is greater than 1, therefore the forces are unbalanced, and therefore we must have an acceleration taking place. If it's an acceleration, then you're going to have a change in velocity. A change in velocity, a change in kinetic energy, then you must have a net amount of work done in the system.
Grade 12 Mindsetters, thank you so much, and we'll see you next week. Bye.